bones told me that the date for exam 1, which was issued to me by the registrar before the term started, consequently that's the date I posted in the syllabus, wasn't right. Too close to the start of the term. It didn't really occur to me, at least the details of which I just announced to you, until Saturday when I sat down and started to write exam 1. I said, wait a minute, what the hell's going on here? Because I'm looking at exam 1 from a year ago, where the material content is far beyond what we could possibly hope to get to if we did the exam this week. And then I looked at the calendar, and it occurred to me, with this ridiculous term starting date of Wednesday, which is already a stupid thing. Now they've given me an exam 1 date, which is also stupid. So with the registrar's indulgence, I will run this class in accord with the way it's supposed to be run, not when they decide to schedule exam dates. So I have taken it upon myself to reschedule this exam 1 for next week Thursday, when the heck it was supposed to have been all along. And I sent a statement to the registrar requesting that they please give us a room for next week Thursday for exam 1. When I find out the room, of course, I'll tell you. But we don't have to be concerned about that immediately, since now we've got till next week Thursday. But for those of you who are concerned about such, or will be concerned about such, I may have said something about this, I don't recall the details. I know that certain of you will have conflicts for evening exams. Another goof by this university. They shouldn't do that. They shouldn't ask us to give exams when many of you folks have laboratory classes or something else. I don't get it. This place was built for education, and that's what the hell it's supposed to support. And it's not supposed to operate with policies that interfere with the smoothness of the educational process. Period. Maybe one of these days, the administration of this university will wake up to this fact. But I'm not sure, because I've been associated with this place since 1967, and they haven't woken up yet. In fact, they're getting worse. Maybe President Machen will hear this lecture. It's on the internet. And if he'd like me to go to his home and talk to him face to face, man to man about this, by damn, I'll be there in a split second. Let him know just how I feel. In any case, we'll let that happen later. Who knows? I might get told to pack my bags. I don't think that'll happen, though. In any case, what I was meaning to say is, for those of you who have a conflict, the policy by which we've tried to operate is to give you folks with an evening conflict with the scheduled exam time, to allow you to deal with the exam earlier in the day. And if I can get territory for such, see, a benefit of Thursday versus Wednesday is Thursday we don't have class. So I can offer the exam to those of you who need to take the exam at an alternate time from 12 to 2 p.m. or 2 to 4 p.m. or 4 to 6 p.m. And that generally accommodates folks with a conflict with evening time. If not, I'll make a special arrangement with you on an individual basis so that, with no serious inconvenience to either you or myself, you'll be able to take the exam. And we'll worry about those individual cases later on. As I said, we now got 10 days till exam 1, and so let's proceed. Now, you may recall at the tail end of last gathering, when I was kind of feeling low, but we did all right. We said, let's take a look at this. Now, before we take a look at this, because this relates to an important consideration which we will now reflect on in detail. Percent ionization. So let's look at percent ionization consideration before we proceed with this. Oh, this before percent ionization. Question 1820. We're still taking a look at analyses of Bronsted-Lowry acid-base equilibrium system, which we are now in position to tackle. We've talked about Ka, how it's defined, what it means, Kb, how it's defined, what it means, material balance, how to get Kas, etc. All of which in some fashion have got to relate to pH. So question 1820. Imagine you have two solutions, both 0.50 molar. Your assignment is to get the pH of these solutions. What information do you need to tackle this calculation? I ask this question because my observations indicate that those of you who have difficulty with this kind of stuff have difficulty because you don't know what a question is asking you really to do. So we're talking to you right now. This question, 1820, what is it really asking you to do? How do you get the pH for these solutions? What considerations do you have to make to get these pHs? Have you got the acid-base table out? You need the acid-base table for all of this stuff. Get it out. Look in the base column. Because any acid-base considerations which we make will involve acids and or bases whose formulas are in this acid-base table. You know, the extended table of which I gave you a copy. This thing. Do you see in the base column the formulas for ammonia and acetate ion respectively? Tell me, which of these solutions is more basic? Which of these solutions has the higher pH? The ammonia solution. That's the base table tells you ammonia is a stronger base. And the molarities of these solutions are identical. So the pH of these solutions will differ as a consequence of Kb values. And ammonia is a stronger base, so it has the higher Kb value. Okay? So to compute the pH for either of these solutions, you need the Kb values for the bases, respectively, ammonia and acetate ion. How do you get these Kb values? You know how to do this. We derived the relationship Kw equals Ka times Kb, where Ka and Kb correspond to a Bronsted-Lowry conjugate acid-base pair. So to get Kb for ammonia, you need Ka for what? Ammonium ion. And to get Kb for acetate ion, you need Ka for acetic acid. These are both in the table. So you know how to get the Kb values. And if you get these Kb values, what general procedure can you now employ? Generalization which we arrived at last time. X squared over m sub I minus x. All done. Right? That's all I'm saying about this thing. M sub I is 0.50 molar. You will find out that either of these solutions can have the hydroxide ion molarity computed correctly by realizing m sub I minus x, a term that appears in the denominator of our general recipe, will be equal to m sub I for each of these solutions. So you cross multiply m sub I times Kb, extract the square root, you get the hydroxide ion molarity, and from that you can calculate pH. All right, 1821. To an extent we talked about 1821 because we talked about pH for sodium hydrogen carbonate solution. But this is ammonium hydrogen carbonate solution. So I'm going to add to this versus pH of 1 molar NaHCO3. Remember what we determined about the pH of this solution? Remember recognizing that hydrogen carbonate ion behaves more strongly as a base than it does as an acid. Because Kb bicarb is 2.4 times 10 to the minus 8, which is bigger than Ka bicarb, which is 4.8 times 10 to the minus 11. If you do this stuff long enough like I do, you'll see the table in your mind's eye at any time you wish. And as I say, for me that's relaxing and pleasant. How will the pH of the ammonium bicarb solution compare to the sodium bicarb solution with the initial molarities of these solutions being the same? You recall we also determined that sodium bicarb solution is basic but mildly so, because its Kb value is a tiny number. Which means even though bicarb behaves more strongly as a base than it does as an acid, its ability to produce hydroxide ion on reaction with water is not very great at all. You can see its position in the acid-base table to realize that. Now then, which of these solutions, or, pardon me, back to the comparison. This solution is mildly basic. It's got a pH above 7, but not greatly above 7. In a while, we'll tackle calculation of pH for this solution, which right now you don't know how to do. Since I made that statement, I'll show you why. Right now, it's impossible for you to calculate the pH for this solution. Unless you've taken advantage of watching the videos for this class when I taught it in the summer. And you've looked at all the videos, which means you know how to do everything. Ha-ha, right? You recall, I'm sure, that when you are challenged with the responsibility of writing equations for Bronsted-Lowry acid-base equilibrium reaction, what do you do first? What do you do first? PSI. The PSI for this tells you the strongest acid in the system is hydrogen carbonate ion. The strongest base in the system is, guess what? Hydrogen carbonate ion. So the principal acid-base equilibrium reaction existing in this solution is hydrogen carbonate ion reacting as an acid with hydrogen carbonate ion reacting as a base to establish an equilibrium between quote-unquote H2CO3 and carbonate ion. How are you going to get pH from this? That's the main acid-base equilibrium reaction in the system. You can't get pH from this. Why not? pH is, by definition, negative log to the base 10 of the hydronium ion concentration. You see the hydronium ion in this equilibrium reaction? And of course, you know from pH you can also get hydroxide ion concentration. You see the hydroxide ion appearing in this equilibrium reaction. So you're stuck. Which means, if you're going to get pH calculated for the hydrogen carbonate solution, you have to look at this reaction. With this treated as an acid or a base. Treated as an acid, you make hydronium ion. Now you got a handle on pH. Treat it as a base, you get hydroxide ion. Now you got a handle on pH. But this is the principal acid-base equilibrium reaction in this system. Which means you're going to wind up with 3 unknowns. Which means, to solve this, you're going to have to pay attention to material balance in addition to the reactions which we have on the board, in addition to one additional consideration, which as yet we have not introduced you to, but will. It's called charge balance. What do you think charge balance means? You know that in writing an equation for a reaction, you have not written an equation unless the statement you have written corresponds to material balance, right? Counting atoms. And what? Charge balance. If ions are involved, you got to have charge balance. Because each and every bulk chemical system is not stable and cannot live if it's not electrically neutral. If a collection of charge of one type was stable, you could go to the laboratory and get a bottle of sodium ions. I had a student in 46 laboratory with me a number of years ago. A long number of years ago. This was back when I was here as a TA. 1968, 1969. Ha ha! Where were you? Ha ha! A student came to me with great frustration. He was in charge in assignment 2 with the responsibility of conducting a flame test examination of sodium ion. You've done this, you're in assignment 2, right? His frustration arose from the fact that he couldn't go to the side shelf and find a bottle that only had sodium ions in it. He says there's sodium chloride and sodium nitrate and a bunch of solutions with sodium ion, but they got this other ion in there. I want to do a test just on sodium ion. So I pointed out to him that the way sodium ions are manufactured is by electron loss by sodium atoms. He knew this. So if the sodium ions were stable and isoluble, then the electrons would also be stable and isoluble. Which means you could bottle up these electrons. You could go to the electron store, the Horvath electron store, and buy a big bottle of electrons. And you go home, you get a big funnel made out of rubber or something so it not affected by electric charge. You take this big rubber funnel and you jab it into the socket. You open up your bottle of electrons. Because in a bottle of electrons, a bottle like that, you know how many moles of electrons be in there? Wow! And you start pouring the electrons into the socket. And the radio would radiate. And the television would televate. The electrons would flow. The lamps would light, and you'd call up GRU and say, "Go to hell, I don't need you anymore." But you can't do that. Because particles of the same charge type in contact with each other are not stable. That's why bulk chemical systems which carry charged species are only stable and will only exist if they are electrically neutral. And we'll have to apply that condition to systems like this to calculate pH. More on that in the future. That's just a seed I planted, because I told you about it. So that when we talk about this in the formal fashion, which means at that time you're responsible for it, you'll say, "I heard about this before. It's not really strange." What's strange about realizing that if you've got a bottle that bears the label sodium chloride, and you find out there's a mole of sodium ions in that bottle, you know there's a mole of chloride ions in the bottle as well. Because if that bottle had a mole of sodium ions and a half a mole of chloride ions, it would explode violently. Kaboom! And away you'd go. Same applies to this solution. But without calculating pH, we can decide which of these solutions is more basic. And we can say something about the pH of this solution from a number standpoint compared to the pH of this solution. What can we say? Is this solution basic, acidic, or neutral? Let's start with that. This solution is basic. How can you say that for sure? It is. Why is this solution basic? Kb bicarbine is 2.4 times 10 to the minus 8. Ka ammonium ion is 5.6 times 10 to the minus 10. You see that in the table, don't you? Which means bicarbine behaves more strongly as a base than ammonium ion behaves as an acid. But how does Ka ammonium ion compare to Ka bicarbine? Ka. Ammonium ion is a stronger acid than bicarbine, isn't it? That doesn't mean bicarb or ammonium ion are strong acids. They are hardly that at all. But ammonium ion is a stronger acid than bicarbine. That guarantees that the pH of this solution, like the pH of this solution, are each above 7.0. They're both basic solutions. But the pH of this solution will be closer to 7.0 than the pH of this solution. Okay? Enough said on that. 1822. I made a reminder here. As soon as you see concentrations and volumes, you can bet that you're going to have to pay attention to PSI on a quantitative basis. You're going to have to get moles of stuff. All right? So let's talk in brief about 1822. The task is get pH. You got the inventories? $100 milliliters, 0.10 molar sodium sulfide solution. We got sodium ion in there, of course. Specifically 0.010 moles of sodium ion. But I'm not even going to write that down because we've come to recognize already, sodium ion, even though it's a metal ion, does not hydrate with sufficient strength to show any acidic behavior in water solution. If it did, since sodium ion is arguably the most common metal ion, we'd have to tell you about this. But if you go to the laboratory, for example, and take 1 molar sodium chloride solution, which got sodium ion in it at a high concentration, given that chloride ion is the conjugate base of a strong acid HCl, so chloride ion is a weaker base than water. So if the sodium chloride solution shows a pH different from that of deionized water, it's got to be because of sodium ion. And if you observe this pH, you'll see it's the same as deionized water solvent. So sodium ion is not doing anything from a pH effect standpoint. So what are the pH affecting species in our sodium sulfide solution? We've been through this before. 0.010 mole each of. Tell me, and I'll write them down. Hydrogen sulfide ion and hydroxide ion. There they are. If you don't get this, there's nothing you can do with this problem. That's why we told you. PSI first and foremost. Because if you don't know what's in the chemical system, you cannot possibly understand the chemistry that the system will show. All right? PSI. Water, hydronium ion, chloride ion. Bingo. From a pH standpoint, do we care about the chloride ion? No. What do we care about principally in this solution from a pH analysis standpoint? Hydronium ion. How much of it we got? 0.010 moles hydronium ion. And if you have difficulty seeing that this solution contains this much hydronium ion, you didn't learn what you were supposed to have learned in 2045. because this is nothing but solution stoichiometry. Now the chemistry that we've reinforced this term is the fact that in this solution there are no HCl molecules. Because that reacts with water 100% extent, you just got hydronium ion, chloride ion. But after you know that, then from 2045 you should realize in 200 milliliters of this molarity, that's how many moles of hydronium ion you got. So guess what? We now have our PSIs, and we write the equation for the main acid-base reaction, which will occur when we make this solution mix. What's that equation? Is our best acid hydronium ion? And our base hydroxide ion. Reaction makes water. Extent, practically speaking 100%. K values 10 to the 14th. That's 100 trillion. I'll take that as 100%. And these were mixed on a 1-to-1 mole ratio basis, weren't they? 100th mole of each. So practically speaking, on making this mixture, we have succeeded in eliminating hydroxide ion and hydronium ion. So we'll strike them from our PSI. So should we now say that the pH for this solution is the same as that of water and call it 7.00? If we do, we're dead wrong because we neglected to pay complete attention to our PSI. Because we still got something in here that affects pH, don't we? And we look at the acid-base table. What do we see about HS minus? It has a formula appearing in both columns. But its position in the acid column says it's a weaker acid than water. So we're not going to be concerned about its ability to behave as an acid in water solution. But how about as a base? Stronger base than water. So HS minus is going to make the solution basic. So now without doing any arithmetic, we know this solution will be basic, and we know it will be mildly basic. Because HS minus should be now recognizable by you as a weak base. But to do the pH calculation, what property of HS minus do we need to have? It's called what? What? KB! Yup! How do we get KB HS minus? We need to use the KW equals Ka times Kb relationship, and the Ka value we want is Ka for what acid?
H2S.
H2S. That's the conjugate acid of HS minus. Now I'm taking a look at the table again. My look says KHS minus H2S, pardon me, KH2S is 1.1 times 10 to the minus 7. Does that look right? How about that? So I'm going to divide 1.0 times 10 to the minus 14 by 1.1 times 10 to the minus 7, so that I may get KB for HS minus, which comes to be 9.8 times 10 to the minus 8. How about that? And so I'm going to write 9.8 times 10 to the minus 8, which is KB HS minus, equals x squared over m sub I minus x. In this case, the x terms correspond to the molarities of H2S and hydroxide ion respectively. As the acid-base equilibrium reaction I'm now looking at to compute pH for this solution is this acid-base equilibrium reaction. Well, you can write that part out. I'm going to go straight to this. Because we just reminded you that for this system, for this solution, X corresponds to the molarities of H2S and hydroxide ion respectively. Now then, what part of this puzzle have we still yet to determine? What is it? X? X represents the great unknown. There's a part of this puzzle we don't know yet. It's called M sub I. What is M sub I? It's the molarity for HS minus in this solution before we have considered this ionization equilibrium reaction to become established. All right, how do we get it? How many moles of HS minus we got in this pot? We had it on the board. I purposely erased it. 0.010 moles of HS minus. But that's moles. M sub I is a molarity. So I'm going to go over here and write equals X squared over 0.010 moles over V minus X. What's V? 0.30 liters. And now we can solve the puzzle. And you see the answer reported in the notes. A solution which is mildly basic. A solution for which M sub I minus X, the denominator, is equal to M sub I. All right? So finally we get the percent ionization definition. It's a simple definition. It's a molarity of a derived species from an ionizing solute, no more, no less. Like for this system right here, clearly H2S is a species derived by HS minus reacting with water. So H2S is considerable as a derived species. For this system, so is hydroxide ion. Because for this system, H2S molarity and hydroxide ion molarity are the same. But if you're doing this computation for this solution, stick with the molarity of H2S. Because clearly that's derived from HS minus in this system. Now, back to the definition. Molarity of the derived species divided by the numerical label on the bottle. M sub I. Whatever it is. Okay? Times 100%. Because this is expressed as a percent ionization rather than a decimal fraction. All right. A couple of exemplary computations. 10th mole of the 2 sig figs acetic acid. We've already operated on this solution. And I recognize that acetic acid, that the hydronium ion molarity and acetate ion molarity are not only equal, they're 1.3 times 10 to the minus 3. So here's percent ionization. 1.3%. You might recall, I don't know, I've reported to you earlier on that for 1 molar acetic acid, the ionization extent of acetic acid is only 0.4%. Because we have realized, as you make the solution more dilute, what happens to ionization extent? Increases. Okay? So that allows us to answer this question. What are the two factors on which percent ionization depends? Well, I could write down dilution factor. But if you want percent ionization to be directly proportional to something, as opposed to inversely proportional, we'll write 1 over M sub I. Does that make sense to you? Because the smaller is M sub I, the greater is the percent ionization. The smaller is M sub I, the more dilute is the solution. So we'll write 1 over M sub I. What else? What else does percent ionization depend on? How did we realize that the ammonia solution is more basic than the sodium acetate solution? What is that? How did we know that the ammonia solution, question 1820, ammonia solution is more basic than the sodium acetate solution? Because?
Acid-base is
What are we looking for from the acid-base table? The Kb values, aren't we? So, 1 over m sub I and K value. The bigger is Ka. For water solutions of different acids at the same molarity, the acid with the higher Ka value is ionized to a larger extent. The acid solution has the solution with the acid with the smallest K value will have the ionization extent the smallest, if the m sub I values are all the same. So, 1824. Given an acetic acid solution contains acetic acid ionized to an extent of 10%. Can we from that calculate m sub I? So now we're taking an ionization extent and using it to get at a solution property, specifically m sub I. Now before we do this arithmetic, I'm reminding you that for 1,000th molar acetic acid solution, the acetic acid ionization extent is 13%. I mean, that follows from what we said here, because this solution is a heck of a lot more dilute than this solution. So we're not surprised to see that the ionization extent is considerably greater. 10 times greater, but greater is what matters. So, the m sub I value we're looking for here, based on the information in that note. Is the m sub I value for this acetic acid solution bigger or smaller than 1,000th molar? Bigger. Because this ionization extent is only 10%. So this solution has got to be more concentrated, right? Got to have a bigger m sub I value. Same acid, so the same Ka value. All right? So we'll write. The equilibrium in question, our general expression corresponding to the equilibrium in question. Of course, in this case, X is the hydronium ion molarity as well as the acetate ion molarity. M sub I is what we don't know yet. What do we write in for X to solve this puzzle? How much of m sub I went away? How much of m sub I went away in this solution? 10% of it went away, didn't it? Does the statement not tell you that the acetic acid is ionized to an extent of 10%? Right? So 10% of m sub I went away, which means at equilibrium, in terms of m sub I, what's the hydronium ion molarity? 0.10 m sub I. And this is 0.10 m sub I. At equilibrium, what's the acetic acid molarity? Well, if 10% of it went away, how much of it's left? 90% of m sub I. So, put it in and grind. That's it. So m sub I divides from numerator to denominator. So you got 0.10 squared. Zero 0.010. 0.010 m sub I divided by 0.90 is equal to Ka. Solve it. Knowing that the value you get for m sub I has got to be bigger than this. I don't really know what the value is. I don't give a damn. What counts is knowing how to solve the problem and understanding the method of solution. I think it's 0.0016, but I'm not, yeah, here it is. I get 0.0016 for m sub I. All right? So we'll finish today by taking a quick look at this one. Because this is going to show us something which we've not yet seen before. And lays foundation for question 18, what the hell is that, 26? Yeah. K, a mythical acid, HA. K is 1.0. What's percent ionization for HA? Here's what we know. Now, what is the aspect of this calculation, which, if my memory is right, we have yet to look at? Aspect. Do you think for this solution m sub I minus x is equal to m sub I? You're nowhere near. So to solve this baby, you got to keep x in the denominator. Now, how should we solve it? Should we treat it as a quadratic and get out our quadratic recipe, which we learned about in algebra class? Not if I see you. Not if you want to survive. You think about percent ionization. And the first thought to make about percent ionization is the thought that gives you the simplest solution for the x squared over m sub I minus x term. Point. Try 50% ionization first. Because at 50% ionization, what's this term got to become? At 50% ionization, what must this term become? It's got to be this. Well, m sub I is 1.0. So half of that is 0.5. So we got 0.5 squared divided by 0.5. Does that give 0.5? 0.5 squared divided by 0.5. Does that give 0.5? Yes. You're damn right it does. How does 0.5 compare to 1.0? Smaller than 1.0, isn't it? What's that tell us? That tells us that speculating on 50% ionization gives a value for this term which is smaller than K. That means this term has to be larger in order for it to be equal to 1.0, which means the ionization extent must compare how to 50%? got to be bigger than 50%. Because this term's got to get bigger while this term gets smaller. That's the only way you make this term get larger until it gets to be equal to 1.0. Answer is 62%. You can call this gee whiz, by gosh, speculation, anything you want. I don't care. But it's the way to do it. Pick it up from this point tomorrow in discussion.